When we measure arc length of a curve with this formula, it's really just a way of using a straight edge ruler on the curve itself. There are at least two good ways to think about this. One, you could think about it as if you're physically rolling your ruler along the curve. This takes skill to execute and isn't as fun as the second way. Two, you can chop your ruler into infinitesimally small sections in a way where your ruler bends like a metal expansion watch band. This way, you can press your ruler to mold onto the curve, and you can then just read the number on the ruler which indicates the arc length. The point is, measuring arc length isn't truly brand new. It's actually a fancy trick on how to use the same old, plain, boring, straight edge ruler. Let's see how. Suppose you want to measure the arc length of the curve f over the closed interval from a to b. And at the very least, you know that f prime is continuous here. But all you have to help you is a straight edge ruler and your ingenuity. Not knowing exactly where to start, you take 2 points x and y from the interval a to b, which are close to each other. Being creative, you write h equals y minus x. That way, y equals x plus h. Trying to measure the arc length of f over the tiny closed interval from x to y, your ruler tells you that the straight line distance from the points x, f of x, to y, f of y, is given by the distance formula as the square root of h squared plus the quantity f of x plus h minus f of x squared. The expression inside the square root vaguely reminds you of the mean value theorem, so you quickly recall that since f prime is continuous on this closed interval from x to x plus h, there exists c sub h in the open interval x to x plus h, such that f prime of this c sub h is equal to the fraction f of x plus h minus f of x all over h. The little h as the subscript on the c simply indicates that we can find a value c for each value h that we want, hinting that we will in fact end up looking at different values for h. I might have said too much and spilled the beans, so I might as well spoil the whole secret. When we take the limit as h goes to 0, where will our c sub h's go? They are stuck between x and x plus h. But when h goes to 0, we see that the boundary wall of x plus h squeezes closed onto x. So our c sub h's will be squished to x as well. Anyway, why did we bother with the mean value theorem? Right, because the expression under our square root looked familiar. So, let's solve for f of x plus h minus f of x from the mean value theorem equality, so that we can substitute it into our distance formula. This is easy, as we can just multiply both sides by h. In this way, we find that f of x plus h minus f of x is equal to f prime of c sub h times h. Finally, substituting this knowledge into our distance formula, we find that the distance between the points x f of x and y f of y is equal to the square root of h squared plus f prime of c sub h squared times h squared. And that's equal to the square root of 1 plus f prime of c sub h squared all times h. This formula has its derivative given by the limit as h goes to 0 of that formula, which is equal to the square root of 1 plus f prime of x squared dx. Reminding ourselves that h is simply delta x, the distance between x and x plus h. That's why we get dx instead of 0. What this means is that our ruler can measure the infinitesimal arc length over the point x. Essentially, we chopped our ruler into razor-thin slices and can put a slice of our ruler exactly on the point x f of x. What's great here is that we can now integrate this derivative to find the true arc length formula. That is, L is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. Simply put, if we use our chopped up ruler along the entirety of the curve, we will be able to measure the exact arc length of f. Amazing! But hey, how come this doesn't just give us back the straight line distance between the points a f of a and b f of b? That's a great question, and I dare you to ask me in the comments below. But remember, we are using our straight edge ruler to measure tiny changes on our curve x f of x to x plus h f of x plus h. And so, as x moves through the closed interval from a to b, we find that our ruler is following the actual curve f rather than bypassing the entire curve just to measure the distance from the point a f of a to b f of b. And with that being said, we find that expansion watchbands are extremely handy when we measure arc length. Just be sure that the links are infinitesimally thin before you get started.